So yeah, I guess that's cool. If you raise your hand, which you can do, for example, like, how do I do that? My problem with Zoom is that I always forget where the controls are. But yeah, Mrityunjay already raised his hand. So nice little icon will pop up here on the name, and I'll know that you raise your hand, and you can then we can discuss. Well, maybe just I don't know if Philip is here. Philip, are you here? Because I think basically the whole review session started with him asking about problem 2.2, and but I guess he's not here. Okay, then I guess I'll do the short intro. So this is the review session for the Moku Moku Math MML book, this book here. And could you, okay, I muted you, Vrinda Brabduch, or did I? Somebody's having some noise trying to, okay. So review session for the Moku Moku math book reading session. And what we usually do is, well, first, yeah, maybe first we should check out the communication channels. Okay, Philip is hopefully, hi, I'm here, I'm in the meeting. Yes, okay, that's here. Wonderful. Great. Then okay, so then actually I will start with you, and then I'll do the whole intro thing because that was my original plan. Philip asked a question about problem 2.2, and problem 2.2 is somewhere all the way in the beginning, and it's about residue classes. And I said that, yeah, sure, that one I can explain in great detail. So this is problem 2.2. So let n be a non-zero integer, positive integer. Let kx be integers, and we define the congruence class of k over line of the integer k as this set. And I'm going to write this down again soon. And then we now define z divided by nz, and this is a question. So what does this mean, z divided by nz? Sometimes written as z subscript n, as the set of all congruence classes modulo n. And so like, okay, what does that mean at all? And then Euclidean division implies that this set is a finite set containing n elements. These are the elements. And then for all elements from this set of congruence classes, we define an addition on them, and we need to show that this is a group. Okay. So Philip, could you, about this, I wrote a PDF. I created a PDF, which is somewhere here in the Slack channel. I marked it. If you go to shared file.
I've read the PDF actually yesterday. And Abel, I want to say in advance, thanks for doing this. I appreciate that very much. You alluded to the fact that we should show that this is a group, and I've just reviewed the axioms for it to be a group. So yes. Number one, we have to show closure of G under the operation. We have to show, this is the second axiom, associativity, so the associative law. We have to show that there exists a neutral element, and we have to show that there exists an inverse element. So if we can prove these four axioms, then we have shown that it is a group.
Exactly. I'm trying to find this in the book so that I can show everyone what we're talking about. And I guess this would be it. So section 241, page 36. And these are the four properties or the four axioms which Philip just defined. And you're absolutely right. If we show that these four things are true, then we solved problem 2.2. So did you have what was the problem you had?
The associative law was shown by you nicely in the PDF you gave. This proof is for me, it's clear. But what is not clear to me, how would we show, for example, closure? And how
Okay.
would we show the neutral element? Because I just have the paper where I did the exercise here. And for example, I have the question that, sorry, this was already B, but yeah, how would we do a closure and inverse and neutral element?
All right, so, okay, let me open my, wait, can I draw here? Where should I draw? Wait, this is my default back. Okay, let's use GIMP. And I will draw here. So let's do something like this, and then this, and hopefully this will be okay. Okay, so first of all, what do we have? We have the residue classes, right? So the residue classes look something like this. So if we have a K, right? And wait,
Emil, I have a short question. What's the difference between a residue class and an equivalence class, or is it the same?
It's the equivalence class is a more general term. So the residue class is a specific instance of equivalence classes.
I see.
I will, but wait, let me write this down. So equiv class versus residue class. I should come back to this. Okay, so the definition of the residue classes was something. Well, let's go back to the PDF so that I don't say anything which is not as in the book. So yeah, yes, okay. So the second line, I'll write down the second line. So we have elements X. So these X elements are integers. And we want to have this property that, well, X minus K, so X minus K, if you divide this by N, and N, I'm gonna put N somewhere here because this is like a global variable. So N, this is the modulus. Okay, so it's called the modulus, and because you always do division, so maybe I will use the first definition after all, because it says if you divide this, so it's written like so mod N, and I'm not sure if everybody understands this notation, what this means. So if you use Python, so in Python this would look something like, so this would be actually a percentage sign. So it takes the remainder. So let me just quickly show Python thingy. So for example, if you take 10 mod 3, what will that be? It will be 1, right? So 11 mod 3, it will be 2, because 3 times 3 plus 2 is 11. And then when you do 12 mod 3, that will be 0. And then if you continue on like this, so you do, for example, I don't know, I in range 10, and then you print every I mod 3, what will you get? You will get repeating 0, 1, 0, 1, 2, 0, 1, 2, 0, 1, 2, right? Okay, so this is what we're talking about. This is the important thing. And so when let's say that our modulus, so here N, this modulus, so N is 3. So whenever we do the division, we always do division by 3, okay? So here, we always do divided by 3. So it means that if we take such a class, we'll have basically 3 classes. One of the classes will be the 0 class, the other one will be the 1 class, and the other one will be the 2 class. And let me just write this again out here. Oh yeah, and if you're using Zoom, be sure to fit the screen so that you see everything. So my top is here at the file, and my bottom is here at near the list. So these equivalence classes are here. And as you can see, these are equivalence classes. So class, that's a synonym for a set. So if you're talking about a class, then you're talking about some kind of a set. So these are sets, okay? So this is a set. Okay, and this is a set, and this is also a set. Okay, these are all infinite sets actually. So dot, dot, dot. And this will start with minus, well, I'm gonna start counting. So there's like -6 before somewhere here, and then -3, 0, and then continue on 3, and then 6, and so on. And then you have here, I don't know, dot, 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 -2. Well, let's continue. This will be 4, and then 7, and dot, dot, dot. Okay. So could you fill out the next one?
Let me think about that for a second. The next should be 5, I think.
Yes, and what would be the one before here?
-1.
Exactly. So this is what you get. And basically, it turns out that this is the same as when you get the equivalence class. So the equivalence class of 0, or the residue class of 0, and the residue class of 3 are the same thing, okay? And this is the same as the residue class of 6, and so on. Another way of describing this set would be 3 times z plus 0. I mean, plus 0, we don't really have to have a plus 0, but I mean, plus 0 is the same as having the same thing. And similarly, this is again, so the residue class of 1 is the same as the residue class of 4 and as the residue class of 7. I could continue writing all the numbers which are here as only with the residue class above. So the difference between this one and between this one is that this is the first one. So this first one, this is the number 1, and this is a set. Okay, this is a set of integers. Is this clear?
Yes, I see.
And then, and anybody else, if you have questions about what I'm saying, please don't hesitate to interrupt or to raise your hand here in the, I will see that in the Zoom channel. So the last one is the residue class of 2, which is the same as the residue class of 5, which is the same as residue class of -1. And this could be written as 3z plus 1. Z is, of course, the set of integers.
Yeah.
Sorry, not 2, but not 1, but 2. And so, yeah, this is what we're working with. And the idea, and this is where maybe I can talk a little bit about equivalence classes, is if you take all the integers, and let's start with -3. So we have dot, 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 all the integers, -3, -2, and wait, actually, let me do it nicely. So -2 will be here, -1 will be here, 0 is here, 1, 2, 3 is here, 4, 5. I think, wait, not 4, 3, 4, 5, and 6 would be here, right? And continue like so. And I'm going to change color so that you see maybe a little bit better what's happening. So this will be green. So this is -2, 1. What's this, 4? And then next would be 7. And then let's do -1, 2, and 3, 4, and then 5 is missing, right? So this is basically what you get. So this will be the pink numbers belong here, and the green numbers belong here. Okay.
So these are all subsets of the integers.
Yes. So what happened with the integers? So if you think about, as like Venn diagrams of when you draw sets, and when you're talking sets, usually one usually does something like draw circles like this, and this actually divided the circle into 3 equal parts. So so you have some of them. So we put, for example, the green dots here, the green numbers here, the pink numbers here, okay, and the blue numbers here, okay. Does that make sense? So, and this is like a nice division. It's nice in the sense that you don't have any overlap. So all these subsets. So there is no point which is both pink and green. Okay. So all the points
are mutually exclusive.
Mutually exclusive, mutually disjoint, exactly. And also you don't have all the subsets, if you look at them, they are non-empty. So for example, if you take 0, 1, and 2, you these elements will be, so 0 is here, 1 is here, 2 is here. So all the, and these are all the subsets, and they're all non-empty. So they have at least one element. And if you combine all these numbers, then you get back the entire set of integers. Okay, so this is what's called a partitioning of a set, and the partitions, they form equivalence classes. So they are somewhat equal in the sense they are equal that they belong to the same partition. Okay, and that sense of equivalence, or the sense of belonging to the same equivalence class, it's very simple to being actually equal. I'm going to mute you because you're making a little bit of noise. Okay.
Maybe if we can just inform people, I just wrote it on Slack, but if you're not talking, it would be really great if you could mute yourselves to avoid some kind of noises.
Yes. And also once again, reminder, so this is our first session, which is recorded. So if you're shy, you can ask questions in Slack. Okay, so let's get back here. So yeah. So in the particular case, when this partitioning occurs like so using this definition, then these equivalence classes are called residue classes. And now comes the kind of maybe more interesting part. It was how the addition was defined. So the addition was defined that if you have two residue classes, residue class which contains the number A and the residue class which contains the number B, and you want to add them together, then what you do, you don't treat them as residue. So you don't treat the A and B as residue classes. So you basically omit the overline, and then you add them together first. And after adding them together, you get a new number. Let's call this number C. Okay, and then you look at the residue class which that C belongs to. Okay.
I see. Yeah.
So it's like number creates set, number creates set, and then we combine the two sets together to get a new set. And this is what we are defining. So we don't know how to do this, but how to do that is that we first combine the two numbers to form just one number, C, and then make a set out of that, okay? And this basically results in something very similar to addition, but not exactly addition. If you want to do, for example, the whole thing in Python, you would define something like add. And well, actually you could do two things. One of them would be define add, and then you have an A, a B, and an N. And you would always do return parentheses A plus B mod N, okay? This would be your function for addition. And well, actually what I wanted to do is something like this. So this would have something like a default value, okay? So you don't expect N to change. You can take any N, but once you fix it, then it doesn't change, okay? Oops, this doesn't work as I expected. But yeah, so for example, you could do something like add, I don't know, 10 plus 20. And that would be 0 because that's 30, and 30 is divisible by 3. Or for example, you could do like add 200 plus 5, and that would be 1. Because if you, and you can actually check this, that it works. So for example, let's look at this. So I don't know if, how clear is this, how the whole thing works?
This becomes clearer and clearer. I have a sub question. I did a short exercise with the following. I actually proved that parentheses, the integers, and addition, because you just alluded to addition, parentheses closed is a group. This, of course, is so. We can prove it by showing that closure holds. I did that the neutral element holds.
Sorry. What was the parentheses?
Parentheses, integers, exactly, and then
this.
plus. Yeah,
okay, so
that is a group, and I've shown that. I've shown closure. You know, you can do that. Then I've shown neutral element, which is of course 0 in this case. The inverse element is of course
exactly
minus.
Exactly.
And associativity holds because of the associative law in addition of addition, which generally holds. And then also showed, and this is a nice thing, commutativity, such that we can conclude that this is actually an abelian group.
Let's review actually what just Philip said. So if you have two integers, a and b, so we're not putting the residue classes on hold. Now we're talking the simple integer addition. So if you have two integers and then you add them together with addition, you will get some c, and that c will be also an integer. So this is closure, okay? So then the next property is associativity. So if you have 3 elements in Z, it doesn't really matter how you add them together. So A plus B plus C. It doesn't matter if you add them together like this first and then A, or if you do A plus B and then plus C. It still might matter if you add the C from this side or from this side, but as we'll see, because it's commutative, it won't matter. The next one was neutral property. So 0 is in Z, and this is the neutral element, because for every A in integers, it will be true that A plus 0 equals to 0 plus A equals to A. So sort of 0 doesn't do anything. And the next one was inverse. So if we know that this is the neutral element, we can define the inverse of every element. So for every element A, we have in Z, there exists, well, it's going to be minus A, which is also in Z. And this is the important part, that it's also in Z, in such a way that if we combine A and minus A, we'll get the neutral element, which is 0. And then finally, that for every A, B. So yeah, up to here, if you prove these 4 points, and these are more or less trivial, if you prove these 4 points, then you prove that this is a group. And if you also prove that AB, I mean, this is, so you just look at it and say like, yeah, we know this about addition and it's true. So this is the last property. So A plus B equals B plus A, again, for every integer in the integers. So in every integer A and B. So if also this is proved, then it's proven, then it's also an abelian group, okay? Yeah, so we want to prove the whole thing for the residue classes. And for the residue classes, well, what are the residue classes? So what was the whole set, which was Z divided by NZ, or sometimes also written as Z underscore N. So this was, how many elements does this have? Well, it has 3 elements, N elements, and the first element is 0. Not 0, but the residue class 0, the residue class 1, and so on, okay? And then all the way to n minus 1. If we look at the example, so when n equals 3, we had 3 elements. We had the 0 residue class, the 1 residue class, and the 2 residue class. So quick question, is the 3 residue class in Z3? Raise your
Yes,
hand.
yes, I think yes.
Why?
Because it's the same as 0.
Exactly. So it is, and it's here. And so in the PDF, I think I gave the proof of associativity, right?
Yes, associativity was proven, and that was very great. I got associativity.
Yeah.
This axiom holds.
Okay, so what you asked about closure. So how does closure work? How do you prove closure here? Well, you take two residue classes, A plus B. Then it means that you have some integer A and some integer B where, so for example, let's look at this example for the, so A and B will be they will be one of these three, okay? So the definition goes something like this. So A plus B over line. And well, so all the, and this you don't even have to think about only the n equal 3 case. You have to think about the whole, I mean, the general case for any n. So when you have something like this, and you know A plus B, so A is integer, B is integer, A plus B is also an integer, right? So A plus B is also an integer. That means that A plus, so let's call this integer C, okay? Maybe that will be easier. And then from this, you can say that C is also in Zn. So I'm not sure if this is clear, why and how. So you just have to say that, yeah, because this was the definition here. And we know that under this line, we will get an integer. Then we know that we'll get, again, a residue class.
I see. Yeah, makes sense to me.
Okay,
I see. Yeah.
So that's closure. So you asked then again about the neutral element.
Yes.
So what was the neutral element for the normal addition for Z plus?
Wait a second, I have to write that down, what you just have written here.
What doesn't change anything if you add it to something?
Yeah, that would be 0.
Okay, you got it, 0. Philip?
Neutral. Yeah, neutral element is 0. Yeah, I got that. Yeah.
Okay, so
yeah, for the normal addition you're asking
yes,
about, right?
And which will be the neutral element for the residue classes?
1, I think, because like the modulus will give you 0.
0 residue class. 1 will give you 1, and 0 will give you 0. So if you divide 0, so again, let's do the Python version. So if you divide 0 by 3, you will get 0. And by division, I always mean that Euclidean division, and you don't look at the quotient, but you get the remainder. Okay? So the neutral element will be the 0 class, or which is the same as the 3 class, which is the same as the 6 class. And to prove this, you say that you take an A residue class, you look at the 0 residue class, you look at the definition, which will be A plus 0. And you know that this addition is the integer addition. So you know from integer addition that this is going to be A, and the line remains. And basically you've proven this is the neutral element.
I see. Yeah, yeah.
And then if you figure out what the inverse, and I'm not going to do this anymore.
Emil, I have a question. In the 0 residue class,
okay.
If we were to add the two sets, can we add element-wise?
What do you mean add?
Like
the plus add.
Let's say we have the residue class 1 with this bar above it, and then we have the residue class with
okay.
0 with a bar above it.
Wait,
then
so 0 with a bar above it and 1 with bar above it, right?
Bar above it.
And
yeah.
then
and let's think about, we have n equals 3. Then we get a set. This 1 is a set and the 0 is a set. And can we basically add this element wise? So let's specify the set 1 over bar.
Yes.
Like this would be I think.
I understand your question. So let's say that we have n equals 3, and in that case, one is -2, 1, 4, and dot, 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 dot. Okay, so an infinite set, and 0 would be all the numbers which are divisible by 3, which would be -3, 0, and 3, and let's add also 6. Okay, so the question is, can we do this element-wise? So something like this, right?
Exactly, yeah.
Sort of. So to be exactly precise, and I'm going to go back to this type of...
Hi,
hi.
Just to help with that question of his, I put an image in the Slack channel.
Let's look at it.
Help for adding and where things go when we add things. Each residue class.
Wait, how do I? Okay, Math, ML, and JSON. But this is not. It's not the one that. This is the circular, right? Yes, the closure property for Z8. It doesn't. Yeah. Okay.
So that means if you get any number from say class 1, which is say 9 is from there, right?
Yes.
And then you get another number from class 2, say 10. And so the sum of those would be 19, right?
Yes.
Would fall on class 3. So since what the residue classes is doing is that it just groups up every integer into one of those on those numbers. As in Emil's example, either you group it from 1, 2, 3 or 0, 1, 2. Because 0 and 3 are of the same class, so it's your preference. So either 1, 2, 3 or 0, 1, 2.
Yes.
Yeah. But yes. I think for finding the remainder, it's easier. I think if we use 1, 2, and 3, so that we know that 1 are every number that has remainder 1 when divided by 3, and 2 is every integer that has remainder 2 when divided by 3.
Yes.
And so if you add any 2 numbers from each class, it's going to fall in one of the 3 classes for sure.
Yeah, so this is a I'm not sure what's the English word. I learned about this in Hungarian, and it's something like there's a compatibility. So as I said, this is partitioning, right? So to divide the whole set, and we have the operation I mean the operation plus. Well, actually, it's the special operation for the residue classes, and the 2 things are compatible in the sense. So this is what just Jason explained. So no matter So if you add, what's the result of this? So let's work through this example a little bit more. So this will be 1, okay?
Yes.
So the thing is that the official way. So when you write something like this, the definition of, for example, 3 times z plus 1 is 3 times k plus 1, where k is an integer. Okay. So basically what this means is that you take z, take every integer, and then multiply every integer with 3, and then you add 1 to all those numbers. And that's how you will get these numbers here. And if you have 2 sets, and when you have this addition, which is something like, this addition is something like a set plus number. Well, actually, it's like here it's int, or actually it's an element. And there's another similar addition which is set plus set. And this is what you are asking. So if this is a set, and this is also a set, can I do set plus set? And how does that work? And that works actually that you add everything to everything. And because you have the compatibility between the partitioning and the operation, you will get a well-defined thing. So when you add everything to everything, so for the small number of n equals 3, there's not many cases. There is only one interesting case. So for example, I think the only interesting case is that 1 plus 2 is 3. 1 plus 2 is, well, 3 or 0 or whatever you want. So 1 plus 2 is 0. And the thing is that if you take any number which looks like this is 1, and take any number which looks like this is 2, you will, and wait, let me just write this down on a nice new sheet of paper. So what I'm saying is that if you take any number which looks like 3k plus 1, and you add another number which looks like 3k prime plus 2, you will have, and this is normal addition, normal everything, 3k plus k prime plus 3, right? And this you can also write as 3k plus k prime plus 1 plus 0. And then you call this, I don't know, k2 prime, and you see that this element here, this is something from 3z.
Exactly.
0.
Exactly.
While,
Yeah.
and
Beautifully explained.
Beautifully explained. I agree.
Okay, so this is how it works. So basically, whatever you had from the integers, it will be also it will also transfer here all the nice properties of integer and addition. Okay.
I see. Yeah.
So this took a little bit longer than I anticipated, and is it okay if we move on to the next question?
Sure. I have just one question. What is then the inverse element in 2.2?
What was the inverse for? So if you had an integer a, what was the inverse of this for normal addition?
Minus a.
Exactly. So if you have a residue class a from Zn, what do you think what will be the inverse of this? The same thing, minus a, only residue class.
I see. Okay.
Basically, you just have to. So that's why I said it's actually mind-numbing substitution, because you just have to add the overline. But you have to take care that you have to know stuff that, okay, you're switching from integers to sets of integers. That's kind of a technical detail, but maybe kind of a nice one sometimes, because if you're working with sets and equivalence classes and partitioning and so on, you can have, so there's a whole branch of abstract algebra which is beautiful, which where you extend this whole idea of residue classes, but to all kinds of different kind of operations and structures. So where the underlying operation, which here was the plus operation, is something more elaborate or something more complicated. It's very cool stuff.
I see. And can we conclude that it is also, I think this is the next question there, then, that it's an abelian group because the commutative law holds for addition?
Yes, and again, it's one-line proof. You want to prove that this is equal to this, and this will be true because you apply the definition, then you apply the commutativity of normal addition, and you undo the definition.
I see. Yeah.
QED.
QED, yes.
QED, yeah, that's nice.
Okay.
Thanks very much, Emil. That helped a lot. I mean, thank you very much.
You're welcome.
I can't say how much this stressed me out, this question, and it was alluded to me nicely now.
Okay. So okay, I want to do a short intro. So I suggested that we start with this problem, because actually I don't really think that it's so important. So from machine learning, I don't think this is kind of think in a mathematical way, because this is more, I guess, maybe a little bit more of a math book than a machine learning book. And this kind of thinking is, so these residue classes, I'm 99.999% sure that you will never encounter residue classes in machine learning and any kind of number theory, because this is basically number theory, or this is basically abstract algebra.
I tend to agree with you. You know, I come from statistical inference. I once, in my master thesis, I simulated randomized controlled trials. I never came across this stuff. You're, of course, right in that regard. But then again, I think we all have the idea here that we want to delve deep into the math. As we know, it's quite important. I don't have to tell you this to you. So I agree there is no direct application, but at least it helps you think in a rigorous manner and way, which is always important in life, I guess.
Yes, so that's what I was trying to emphasize here. So that that basically you could say that, well, yeah, just add the line, remove the line, apply the so all this. So this is the whole idea for all the proofs, if you want to go. But the main thing why I think they included this as an example is to try to force you to do the mathematical way of thinking, which is always like go abstract and go like. So to be like really extra clear what something means. And especially in the first few chapters, or maybe just the second chapter, where they talk about like what's the direct product, and that it can be also not direct product. Sorry, but the dot product is a special case of inner product. Yeah, so inner products, that they can also be generalized in this sense that, okay, and so this whole idea that we don't really specify exactly what something is has, only we just specify some certain desired properties, like for groups, for example, like the closure and the associativity, the neutral element, and so on, which was an example for the group. And the same idea and the same way of thinking applies for inner product spaces.
But this calms me down, that in the sense that it was a hard exercise, and it was for the pure mathematicians in a way.
Yes, it was totally a pure mathematical kind of an exercise. So no, not at all machine learning kind of thing. Okay, so let me do just a short intro. So this is the review session for the MLT Moku Moku math. What's the name of the book? MML book. I always just call it MML book.
MML book, I think, is fine. Yeah.
So for the MML book reading session, which is a bi-weekly, and Moku Moku is a Japanese word for like a silent study session. And what we do here is that we read for 1.5 hours for anybody who is new and doesn't know. Maybe I should point out, so the entry point is the Slack, I think, in some way. And usually in the Slack, most channels have some kind of a topic set. So here I set the Zoom thing, and also some information. The other important point is, I guess, the meetup page. So meetup.com is like a service to arrange meetings or meetups, or like, hey, we have some kind of a meetup and some kind of a gathering, who wants to join? So that's a general site for that. And Machine Learning Tokyo has their own account, and they announce events there. Machine Learning Tokyo is a Tokyo-based group. I'm not sure, maybe so maybe Susanna should interject here to exactly state the motto. But wait, no, I'll do it. So if you go to general and then you go to here, and yeah, you go to the starter kit. So this has a very nice GitHub page where you have all the basic things you need to know about MLT. And yeah, so you have the mission. So the mission is to democratize machine learning. So MLT is an award-winning nonprofit. Sorry, I'm not sure how to read it. Domo. Dedicated, it's basically a non-profit organization, right? Yeah. So dedicated to democratize machine learning through open education, open source, and open science. MLT supports a research and engineering community of 4,500 members. So yeah, I guess the 4,500 members also includes the non-Tokyo based and non-Japan based members. So you don't have to be in Japan to be in MLT.
Yeah, and I think we're almost 5,000 now.
Of the Git commit. What we'll do today, yeah. So we'll do discussion. So I really enjoyed the discussion with Philip, and please, everybody else, if you don't understand something, interrupt and ask like, wait, I didn't get that last part. So sometimes I speak too slowly and I become boring, but sometimes I speak too fast and people lose track. So when that happens, I mean, both of those, when it happens, please like encourage me like, yeah, this is clear. And also when I'm too fast, and this is generally true for anybody who's talking about mathematics. And maybe just what will okay, I think that's more or less everything I wanted to say about general introduction and the session, and a little intro about myself. So I'm I'm complicated. I'm also both from Serbia and from Hungary, but I studied in Hungary at the university where they have quite high standard for mathematics. I did computer science, but with huge amount of mathematics. And then I ended up there doing my PhD and then also teaching there. And I was teaching mathematics, if you didn't guess by now. So yeah, I'm quite mathy. So in that sense, I don't know, I'm maybe very well suited for this or very badly suited for this, but anyway, I'm gonna try to be quite mathy in the sense, but I guess it's okay because the whole book is mathy. Does anybody else have any questions right here, right now? So, oh yes, maybe one more important thing. So if you go to the meetup page of MLT and then look at the, wait, where is, oh, Susanna, where is the summary of the, what we'll do for the math reading session? But I think it's on each of these. Wait, if I go here, will I see the page which I want to show? Because we covered now. So here in Japan, we covered. No, wait,
There is another blog post if you're referring to that.
Yes, I think I'm. This is it, I guess.
I think so, yeah.
Thanks. So yeah, I want to show the plan. So when, and where are we? So yeah, this is the plan, what we want to do. And where's this nice picture? Oh, this is wonderful thing. Susanna, I think you did this, right? So this is excellent. So this is like when and where we are with the sessions. So we had up until now 6-7 sessions. So basically we got to linear regression, which is chapter 9. We didn't do that yet, and I think we are like the first, because we have different time zone. We have a Indian time zone and then American time zone, I think. Am I correct, Susanna?
Americas and EMEA as well.
Yes, and they will be doing, so we already did chapter 8, and they will be doing chapter 8. The India time zone will be doing it today, and the Americans will be doing it also today, but their timeline, it will be our tomorrow, right? And so yeah, this review session is, so what we did was the first chapter of the second part, and this review session is basically the review of the first part. So all the mathy things. And I think that's basically all about the intro. Maybe one more reminder that this is the first time that we are recording the whole thing, which is nice, new and exciting, and because a lot of people asked about it. And well, I guess let's move on to the next question.